Okay, so last two lectures we went through the basics of orthogonal range searching. We saw two data structures for how to do it, specifically KD trees and range trees. And we also saw how you could, in some more general sense, modify either a range tree or a KD tree to become a dynamic data structure, and also how you could speed up range trees a little bit using fractional cascading. So this time, we're going to look at the inverse of the range query problem, or the kind of like the opposite. So in the range query problem, we have a bunch of these boxes, and we have a bunch of points, and then we're going to take a box and then locate all of the points which are contained in that box. Today, we're going to start with, instead of a bunch of points, a bunch of boxes. And then we're going to take any old point. We're going to locate all of the boxes that are contained in that point. So it's the opposite of the range query problem. And so these types of queries are called stabbing queries. We'll see a couple of other variations on this. But for now, we're just going to look at specifically this problem of locating all of the boxes that contain a given point. Right? So that's the idea. So it's just the opposite of what we've been doing so far. So, OK. Right. Oh, no. OK. Maybe I'll try the other expo markers. We'll see if that works a little better. No, maybe this one will work OK. Yeah, that looks all right. Yeah, I have a theory that these whiteboard manufacturers formulate each of the markers in their whiteboard so that they're not compatible with one another. So if you use the wrong one, it'll create some weird streak or something. But anyway, we're not going to worry about that. I hopefully won't have to erase the stuff at the top, and whoever comes in here next is just going to have to worry about that issue. So anyway, OK. Right. What's a stabbing query? OK, so here's the input. So we're going to say that we have a bunch of these boxes, which we'll write as uppercase R. And this is just some set, R0, R1, etc. R2. These orthogonal ranges, right? So we have this collection of orthogonal ranges. All right. That is, if we take any of these Ri's, this is going to look like a Cartesian product of intervals. So we could think of this as basically we'll have some little R0i. Call it minus R0 I plus R1I. We have a bunch of them, but there's sort of D of these boxes. So we have RD minus 1I I plus. Right. So that's the concept. Again, same thing as before. They're just ranges, Cartesian product of intervals. And a stabbing query, right? Or we'll actually call this a is just something where we'd say, OK, given some point x in Rd, find all Ri in R such that x is contained in Ri. Right? So that's the idea. This is just like the inverse version of orthogonal range searching. Seen this before. No big surprises there. Okay, so that's sort of what we would like to do is pre-process all of these RIs into some kind of data structure which will support fast stabbing queries. So we want to basically pre-process our stabbing queries. I mean, obviously, we could just do nothing, right? And then checking if a point is contained inside one of these boxes is, an order D operation. You just check that it's contained inside each interval, and then you're basically done. So you could do this in order D times n time without having to even think about it. But we would like to say, OK, fix this set of rectangles and speed up these queries, right? I mean, which is a reasonable thing. I mean, maybe you would have like some sort of map or something which is made out of boxes. You want to be able to quickly locate whichever point happens to be contained in one of these boxes. OK, so that's the general D-dimensional picture of what we would like to do. But before we get too far ahead of ourselves, let's look at how this would work in 1D. And this is actually a little bit tricky, right? I mean, in the case of the sort of 1D interval query, that was for just getting a range, scanning through all the values in a sorted list. But this is a little bit harder because we have a list of intervals. And so we want to locate the point inside this list of intervals. And now this gets a little complicated. So let's go through the details of that first. So we're going to look at 1D stabbing queries, right, where all of our ranges are intervals. That's the first step here. So we're going to look at, for now, 1D stabbing queries. All right. So our input is going to be now, instead of a collection of boxes, a collection of intervals. Or we'll just write them as, say, I, 0, 1, etc., up to in minus 1. We want to process for fast point stabbing. All right, so we're going to say, OK, given a single point, locate all of the intervals that contain that point. Now, we're going to see two different ways to do this. The first of them is going to be, in some sense, a little bit faster for this problem, and it will also generalize more naturally to the higher dimensional version. And so it'll seem like this is a much better algorithm than the second one, which we'll go into. And in practice, for solving the problem which we just described, it certainly is. But the second approach to this problem will turn out to have some nice alternate applications, which we will then look at, right? So that's basically the idea. So we're going to start from this 1D version. We'll see two different ways, and both of them will turn out to be useful for different types of applications. But let's start with, and this is a data structure called an interval tree. All right. So interval tree. So here's the high-level idea behind an interval tree. So suppose we have some collection of intervals. All right, I'm drawing them kind of stacked on top of each other, but you shouldn't read anything into that. They're just intervals on a 1D line here. All right. The only reason I'm doing that is so that we can actually tell the difference between them. Right? Or something like that. OK? I'll probably want more space over here, so I'm not going to draw that guy. All right. So the basic idea behind an interval tree is that we're going to take the endpoints and sort them along, the real axis here, right, where all of these intervals are defined. And then we will find a bisector which cuts these endpoints. Which happen to cross it. So basically, given some point, so suppose we select this point here as our median for splitting the line segments. What we'll do is we'll take all of the line segments which are to the left of this median, right? They don't cross it. So that would be like these line segments over here. They're going to go sit inside some other tree, to the left of this node. Similarly, all of these line segments over here to the right of it, they're going to sit in their own tree off to the side. And then the line segments which happen to cross will get stored in the node of this tree. Right? And so this is the sort of high-level idea, is that we're going to just recursively iterate this decomposition here. I guess I should probably. So we're going to basically iterate this decomposition until all of these line segments are classified into one of levels of the tree. And the way that we're going to search this tree is that we'll basically take whatever point we're going to be querying or stabbing through the tree. We'll first search within the root node of this tree, right? So the line segments which are stored in the middle. And then if there are any line segments, if the point happens to lie to the left or to the right, then we recurse down that subtree. So that's the high-level idea. So there's sort of two real tricks to this, right? The first is that we have to basically make sure that this tree doesn't become too large or that it stays relatively balanced in some sense. And the other one is that we have to make sure that when we get to these middle levels over here, that we have some way to efficiently query these middle levels, right? And so that's the basic idea, right? So let me try to write this out in a little more precise way. Right? So here's the concept of how we construct a node, right? And it's going to be easier to just write this in code, I think, rather than try to sort of describe it. And then I'll say what sort of invariants we have to define. So let's write this function here. We'll call it create node. The input here is going to be some set of intervals I. All right? The base case for the recursion is we'll say if I is empty, then we're just going to return null. Like, don't do anything, skip it, right? Otherwise, we're going to find this midpoint, right, which will basically be the midpoint of all of the line segment endpoints, right? So find median of endpoints. All right, and you can do that, in order and time using quick select. All right. Then we're going to basically split I into these three different parts. We're going to have this region down here, which we will call I left. This region here, which we will call I middle, which we'll call I mid. And so we're going to build these things by doing a loop over all of the i's. So we'll just start out by initializing I mid, I right. Just initialize each of these things to empty arrays. All right? OK. So now we're going to go loop through all of the intervals in I sub j. So here, and let's actually let me write it this way, right? We're going to write the intervals as basically a b, right? So we'll work with the components of the intervals here directly, right? Yeah. So there are three cases here, right? So we'll say if b is less than mid, then we're going to go stick this thing in I left. Similarly, else if a is greater than mid, right? So it's to the right of the whole split point that we've selected here. Then we're going to go store this interval in I right. Otherwise, we're going to stick it in the mid interval. OK. All right, so we now split this thing into 3 parts, and now we need to build the final result that we're going to return. So for the result of this algorithm, we're going to return a node, all right? And it's going to have 4 properties, all right? So I'll say keep track of mid that we recovered. Similarly, we're going to have to store the left and right subtrees, right? So we're going to have these 2 children. So the left will just be create node of I left, which is going to be create node of I right. And so this handles the case where we would like to go search for this point inside this interval, and we have to look to the left or to the right, and then we just sort of march down the tree and keep going until we finally located some node that it happens to be contained in. But I haven't told you what we're going to do with these middle points here. So here's the idea for how we'll deal with the middle points of the tree. What we're going to do is we're going to build 2 separate arrays, right? Or we could also think of them as trees, however you would like to view this, which will sort all of these segments by their left and by their right endpoint. So the first of these 2 trees is going to sort these arrays by their left point, and we'll call this tree left assoc. Or this is basically like left associated tree, or whatever. We're going to create a tree here which will be called, wow, that's also really, really bright. Okay. All right, that one looks a little better. We'll try that. So we're going to store an array which we'll call left. These are just going to be segment sorted by their left endpoint. And we're also going to store another version of these trees for the intervals sorted by the right endpoint. Right? And these are basically, this is just I mid sorted by right endpoint. This is just I mid sorted by left endpoint. And so the tree that we're going to store down here, in addition to having these first 3 properties which we've written, it's also going to have 2 extra properties here. Which is basically going to be what we just wrote. We'll write this as sort I mid. We'll write begin for the left point or whatever, and then right, kind of running out of space. Sorted by the endpoint. OK, and that's it. So this subroutine, right, if we call it, will completely construct an interval tree. All right. So let's say a few things about the properties of such a tree which is constructed in this way. I mean, but for a starting point, though, let's observe 2 things, which is that, first of all, when we split this tree into the left and right endpoints, because we split it by a midpoint, each of these 2 subarrays here are going to be size at time we run this algorithm, we would have to basically execute n over 2 operations for the left subarray, and then n over 2 operations for the right subarray, and then plus however much time it takes us to process all of the nodes in the middle, right? So the cost of the number of like levels of recursion that we can go through here is at most order log n, right? So the cost of traversing this thing will be order log n plus whatever our times however much work that we have to do inside each level in order to process the middle section of the array, right? So finding the middle point of the array, we can do this in order n, right? And we can actually discount the cost of sorting these two subarrays by basically what we would have paid to construct the two other. We can just not charge that to the traversal of the trees going farther down. So the total cost of running this, assuming that we use a fast median finding algorithm, will be order n time complexity of this algorithm. So this is our pre-processing time. The size of the tree, if we think in terms of the total number of nodes here, is going to be at most order n, because each interval will be stored in exactly one node, right? I mean, we might have to store 2 copies of it when it hits this midpoint here, but it will always be owned by exactly one node, right? So the size of this tree in total is order n. So our size is order n, pre-processing time is order n log n, and then the height of this tree is at most order log n. It could actually be smaller if all of the nodes happen to be stored in like the root, right? So if we have a lot of nodes which happen to be packed into like the center of this whole thing, then okay, maybe the tree happens to be very, very short. But the farthest down you can ever go in the tree is at most log n levels. So we have something here which looks an awful lot like a balanced tree, or at least it has all of the properties that we would care about in a balanced tree. It using an n log n time, right? So this looks like we've done something reasonable here, right? Construct this tree. So let's look at how we can now do a query on this data structure, all right? So, okay, here is the high-level idea, right? What we'll do, if we want to query a point on this interval tree, is, let me kind of erase this stuff here. It's a little bit cluttered trying to draw all of it. So if we want to query a point, the way we do it is we start from the root of the tree, right? So suppose we have a point that comes down here, like that, right? So starting from the root of the tree, we first do 2 things, right? The first thing is we do a search on the left endpoints of the tree, right, in the left associated array, to query all of the intervals which happen to intersect it, right? So we basically take the point. If it's to the left of the tree, search in left associated array. That'll report all of that point. Until we've, eventually. We do a search on the right associated array in the tree. We've exhausted all. So the cost of doing this search here is basically order log n, but we can actually charge each of those because every operation that we do in this search, if we march over this sorted array in order, is actually going to be one interval that will ultimately be reported. And so that's basically a free operation, the search in the we're all done. Log n. Log n plus the query is order log n plus k. There's also the degenerate case if our query point happens to land exactly in the middle. If that's the case, then we're actually done because we can just report either the left associated array or the right associated array, and that's it. So this is pretty good, I would say. In fact, this is actually optimal for this interval size and pretty much as awesome as it gets, right? And so, okay, are there any questions on this before I move on to the next point? All right. So does everyone kind of get the idea for this data structure? I mean, there's sort of two kind of interesting moving parts, right? We have just a normal kind of binary search tree here, but then we also have these extra little arrays hanging off of it. But does everyone get how that works, right? So we're all clear? Good? All right. And this querying procedure, everyone kind of understands this idea, right? OK. So now what we've seen here is we can use this to do a point stabbing query. It turns out that we can actually maintain the same time overhead and also support an interval stabbing query. So as a sort of generalization of this, we could imagine that we have a bunch of these intervals out here, and then we want to query them with another interval. So this actually generalizes both orthogonal range queries and stabbing queries with like a point and a bunch of intervals. Because you can imagine I could just make all of these intervals to be like trivial intervals that contain exactly one point, and then I can now do an orthogonal range query. Or I could imagine these are all intervals, and I'm querying with a trivial interval. So this would just be a stabbing query, or I can do anything in the middle, right? So this is sort of a 1D general stabbing query. 1D interval stab, right? So this sounds pretty cool, because if we can do these queries fast, then we can do every query that we care about in this sort of orthogonal range searching paradigm fast, right? And it turns out that this data structure allows us to do this in 1D pretty efficiently, right? And we'll now go through the details of that. So I'm going to erase this construction algorithm here, and we'll write it up. And it turns out this is actually really easy, right? So here is how we'll write this. We'll write it as basically query. It'll take, or actually let's just call this stab. We'll take a node as input, and then we'll take the two endpoints of the interval. So this is basically stabbing it with some interval a, b. Right? So we're going to take this interval and then thing. Right? So there's basically two steps to this, right? So the first thing is we have to deal with the recursive part of it. So we'll say if this interval happens to intersect the left side of the tree, that is, if a is less than mid, right? So if the left part of the interval overlaps here, then we have to recurse into the left tree. So we'll basically call stab I node dot left a b. Ditto for the right side. So if b is greater than mid, then we have to stab the right side. Stab I node dot right a b. Right? And now we have to deal with the stuff in the middle, right? So there are basically three cases is if on the left associated. Report range, right, which we're going to just say is something that will just report all of the elements in the left associated array, which happen to be less than b, right? So this will be in node dot right assoc b, right? So this will just report all of the ones. Let's maybe call it report range LT for less than, right? Otherwise, if it happens to be to the right of this whole, it should actually be the left associated tree, right? So report range LT left associated tree B, right? Otherwise, if this interval here happens to be to the right of the midpoint, then we'll do the search on the right associated tree. So this would be if A is greater than mid, then we'll do GT node dot right assoc A. So it's basically just the opposite of the thing that we would do if it was all to the right. And then finally, we have the case where it happens to cross. And this case is trivial because it just means that all of the intervals stored in the midpoint of this node are going to cross this range that we're recording. So we can just report whatever. We can report the left associated tree. We don't even have to search it, don't do anything, right? So let's look at this, right? So this algorithm here, right? These two cases are exclusive, right? Because basically, all right, well, they're not exclusive, right? But the way that we can deal with this, right, is that if it happens to split both of these two edge cases here, right, we can think of this as basically doing like a binary search on A and then a binary search on B, independent of one another. And so in these cases where we have to basically bifurcate, we can just charge one binary search call stuff here, right? But if we actually happen to hit one of the nodes inside the interval range, right? So the complexity of doing this, right, is going to be logarithmic in the size of the data structure, right? So we have to basically pay order log n, for the overhead of the query. And then there's going to be an extra k factor again for reporting all of them. So this, again, runs in order log n plus k. So this is sort of the general, super duper better version than range searching query, right, that we can do in 1D, right? So that's the idea, right? So, okay, are there any questions on that, or is that clear, right?
So report range. So you got report range left and report range right.
Report range like less than, right? So what we want to do is we have this, right? We just need to report this thing. So we have to basically find all things which happen to be less than B, right? So we have like all these endpoints. We take our segment search all things which are less than that. So all predecessors of the right endpoint, right? Similarly, if we have something where we find basically like the left point here, right, then we can just search all of those, right? That's it. So that's the whole idea right there. Pretty simple, really. I mean, it's I think relatively clear what's going on now. So okay, so that's interval trees in 1D, right? Any questions on that, or any other questions? All right. Okay. So now we're going to see how we can take this 1D data structure that we have right now and then generalize it to work in any dimension. And the basic technique that we will use to do that. So I won't build enormously trying to figure out how to draw this thing, but it's actually easier just to kind of explain it. Use, right? Right, so we have order n size, n log n pre-processing, and log n plus k query for interval stabbing, right? Which basically is the most general kind of query that we have in this setting, right? So that's all good, right? Okay. So now higher dimensions. The high-level idea is we use that same trick that we did with range trees, right? We use this concept of a dyadic decomposition of an interval to basically build up lower dimensional interval trees from one interval tree. So it's sort of the same idea as the range tree, right? Same idea as range tree. basically dyadic decomposition plus recursion. That's one way to think about what's going on. For each as covering some collection of intervals in this underlying set tree, it would cover. Similarly, this node here will basically cover all of these intervals and whatever intervals are going to be stored below it, and so on, all the way down there. So if we have some collection of intervals, splitting up this whole line here, we can then decompose them into families of intervals which are covered by these nodes in the tree. All right? And the idea is that we'll take, for each node in the tree, all of these intervals, we'll recursively build another interval tree on each of those separate dimensions. So if we have some boxes, right, we'll basically split them up into 1D intervals here along each of these things, and then each node in the tree will then correspond to all of the higher dimensional intervals, right? So we'll have sort of the first component. Then each of these things will build trees for their second component. So this would be sort of like the projection onto the y-axis. This is the projection onto the x-axis, etc. So we're just going to keep projecting onto. So yeah. Start by building an interval tree over first component, say, x, right? Then at build interval, we'll say build a d minus 1 interval tree. So we'll start out by building a 1D interval tree. So this is how we get to d-dimensional interval trees. So to build a d-dimensional interval tree, we're going to first build a 1D interval tree, then build a d minus 1 dimensional interval tree for every node in 1D tree. But there's just building interval trees for all of the nodes, which happen to be for all of the intervals which are below some node. We're going to basically split the nodes into two types. So we're going to have all of the nodes which are contained inside this tree, and then we also have to do a second set of interval trees for the left and right associated trees. So we're going to basically split them up into three parts. So we're going to have the sub-intervals, we'll have the left associated tree and the right associated tree. And this will increase the number of intervals that we have to store by a constant factor. All right? So we'll now be storing like maybe 4 times as many intervals or something like that per each level of this tree. But it's only a constant in d, right? And so we're still going to end up being exponential in d at the end of the day. But it will all come out as basically like an n log d minus 1 n type tree at the end of the day. So at every node of the tree, we have to recursively build one of these d minus 1 intervals. Right, and then children. So that's the idea, right? And so for the left associated array and the right associated array, remember how we can think of those things as binary trees again. So we can do the same idea. So we take the left associated array, we basically split it up into intervals, thinking of it as a tree. For each of those trees, we recursively build an interval tree on that set of intervals, right? And that's basically it, right? So that's our new data structure. To query it, start from first interval, split into intervals in just the same idea as a range tree, right? We started from some query range. In this case, we're going to start from some query interval. We'll take that interval. We'll figure out, which of these trees it happens to cover. Higher dimensional component. And you just keep iterating that all the way down until same as range trees, right? So we end up with something where the pre-processing time will become log d minus 1, or n log d, I guess using this system. This will run as n log d minus 1 n size, and then the query time will go up to n log d minus 1 if we use fractional cascading again. So it ends up basically giving us exactly the same performance characteristics as we would get out of range trees, though it's a little more complicated because we have to, sort of iterate this range tree thing multiple times, and there's a lot of extra pointers flying around. But it's not so bad, right? I mean, this is a little bit messy to kind of write in prose or try to draw a picture of it, but it's relatively straightforward to just write a computer program that would do this, right? So this is sort of the general range searching data structure that we would have in higher dimensions, and this is pretty much as good as it gets. So you could also then combine this with some weight balance augmentation to make it dynamic, and then you can do all of your insertions and updates and whatever as fast as you would like. Or you could use whatever other techniques that we've seen so far for range trees and just apply them right here. So this is sort of the sort of general range searching data structure. It'll just work for whatever purpose you'd want. You could even use it as a drop-in replacement for range trees with just constant factor overhead. So okay, so that's interval trees. Any questions about that? Right? It's just range trees applied to interval trees. That's all that it is. Right?
What's the space complexity?
What?
What's the space complexity?
Log d minus 1, n log d minus 1 space. So exactly the same as what you end up with for range trees. Better, because they allow you to answer these interval queries. However, they're also going to be using this extra amount of space because you have to store intervals. So in practice, maybe it's a little more mess to deal with it, right? But in a sense, if you have one of these, right, you could, in some theoretical sense, get away with not having a range tree. So that's the okay. So that's kind of it for that approach to data structures. So now we're going to see a slightly worse way to do this, but it will turn into something that we can use for some interesting alternative applications, which aren't so well covered by this data structure. So this is sort of, we'll start from the 1D problem again, right? And we'll see a kind of crappier data structure. I mean, it's covered in many textbooks and many places talk about it, so it's good to be aware of it, but it's not quite as good. But it can do a couple of things, which are kind of neat. But it's going to at first seem like, why are you bothering with this stupid thing, right? Basically say we have some set of intervals, capital I. I'll just write like this. 0, I1, etc. And again, in 1D, right? So we're just going to start from the 1D case here, not worry about higher dimensions. And so here is another way that we could think about grouping these intervals together. It may be somewhat conceptually simpler. So suppose we have our intervals here. I mean, one idea, right, at first, would be, okay, what if instead of and then do a trick kind of like we had with the slab decomposition. All right, so we're going to basically say we've got these endpoints down here. Endpoints here, splitting up the real line into contiguous regions, right? So it's same for this point here. I know all the intervals above it. Same, etc. Right? So I could take these points here on the line, and I could build a binary search tree out of these points, and then use that to locate the intervals. Right? So I could say, okay, start with this point here. Maybe it goes down to there. So maybe I have a tree. It looks like this. All right. Now, if I want to locate all of the intervals which happen to cross any given query point, I can just locate through this whole tree, and then eventually I'll find them there. And for the sake of completeness, it might be nice to kind of augment this thing with a negative infinity and then a plus infinity point here. So I'll actually want to go stick an extra node there for infinity. Here, so this is how we'll draw the connection. Right. So that's the idea. And then each leaf node of this tree, we can think of that as corresponding to the interval immediately to the right of it, for example. So I could actually remove the plus infinity point and then just think of it like this. Yeah, so if I think of each of these nodes here, this node, in a sense, corresponds to this interval immediately to the right of them. So if I want to locate them, I could do a search on the tree, find that interval, and that would be done. Or I could expand it all the way out, to all of like the leaf nodes of the tree, and then each leaf node would be like an interval directly. So interval here, two intervals, interval. Right? Actually, thing, I don't actually need it. I can just store these like sort of leaf nodes. So this is going to be this interval, 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 interval. And within each interval, the number of segments that I have, or the number of intervals I have above it is constant. So one kind of dumb idea is I could take all of the intervals which are stored in here, stick them in a big list, right? And now if I want to do my query, it'll be really, really fast, because I just have to walk down this tree, find whichever leaf I'm contained in, and I can report all of the segments or all of these like little intervals above me directly, right? The time complexity of doing that will be order n log n, because I have to do the initial query, which will be log of the number of nodes inside the tree. But the size of storing that will be quadratic, right? So the sort of dumb idea is basically store intervals in leaves, right? We get order log n plus k query, which is really fast, but we're going to pay for it in space. Well, that's no good, right? This is basically the same idea as something that basically works like that. So here is the idea. It'll allow us to go from n squared space to n log n space, which actually isn't any better than what we did before. It's actually worse. Of that dyadic decomposition trick. All right, so here is the idea. So what we'll do is for each line segment, we're going to store it in each of the, we're going to, instead of storing this list of all of the line segments at each leaf, we're going to store them in the nodes of the tree, right? So here's the sort of slightly smarter idea, still maybe kind of dumb in light of what we've already seen. is to basically store segments in nodes, not leaves. And the idea is that just order log n nodes if we split them up into a set of intervals, which will cover it, right? So the idea is that if we take any segment here, this segment is covered by this interval down here, this interval, and this interval. So I could just store it in this node of the tree, and I would be done. Similarly, for this segment here, right, I could look at it as covering this interval down here, and then also these intervals. So I could store this segment here in this leaf node plus the node for this tree, right? So I'll draw the pointers for these things in this way, right? So stored there. This whole segment would get stored down there, and it would have another pointer down there. Then finally, this node here, well, it's going to be stored in the, I guess, left node, or the left here. No, actually, this thing should actually go all the way down here. So this one will be stored in that node here, and then also this tree down here, right? So that's kind of the idea with this, right? So we'll basically take each of these segments and then store it in these nodes of the tree that happen to cover the input interval. The conclusion is that each segment is order. Right, so we only have to store at most order log n extra pointers or copies of this interval sitting around, right? And so we can still use the same kind of query idea, right? Where if we do this traversal, we basically say, well, OK, when we get to a node, we then report all of the intervals that happen to be contained in that node, and then continue recursing down the tree. So we'd have the same query complexity. And the space storage here would then just go down to order n log n. So space becomes order n log n. OK, well, that's kind of a neat little trick, right? But it turns out that we can actually use this data structure in sort of the same way that we used a slab decomposition to store segments. And so we can use this technique. Maybe it's not so great for intervals, right? Because we have, if we're willing to pay this extra log factor in space here, then this actually turns out to be a kind of simple way to get reasonably fast queries for point location problems. And we can also use it to answer another kind of interesting query in 2D, which is a windowing query. So what do I mean by that, and what's going on with this whole thing? So right, let me draw a new kind of data structure. And we're now going to move on to a different problem here. So we're no longer going to be talking about stabbing queries.
This is signature, right?
Yes.
And
It's
how does it do like a range stabbing query, or can it do that?
You can, but it's not. Well, you basically have to take your input range, break it down into intervals, and then you have to query each of those intervals separately in your range, right, when you get that. And so when it's the same way that you take one of these input segments and then query it separately. The disadvantage, though, is that that won't actually be a log n operation, but it will end up being log squared n. Right? So it's not actually quite as good. So there's basically this extra log factor sitting around here with everything in segment trees. They are, for the purposes of stress this, that this is actually not a great data structure for intervals, right? But it's a fine data structure for windowing queries, which is the other thing that we're going to look at right now. So this is the idea of a windowing query. Again, we're back to segments, right? So we're going to say, given a collection of line segments are 2, right? Right. What we would like to do is to pre-process these line segments so that we can support windowing queries. So we want to pre-process segments to support fast windowing queries, or window queries. So here's how this will work, right? A window query is just going to be some orthogonal range which happen to be contained in that window, right? I mean, we'll also see that you could use this data structure as well for doing point location queries, right? So a point location query, as we remember before, is basically a vertical ray query. So we take a point, we shoot a ray up, and you report the very first line segment that you happen to hit, right? We don't want to care about all of them. We just want to get the very first one. So these are the sort of two interesting things that you can do with the segment trees. You can do windowing queries, and you can do a vertical ray query, right? We'll be able to do both of them in order log squared n time, right? And the way we do it is really, really simple, right? We basically first build a segment tree, which is that data structure that we just went through, on x-axis projection of segments. All right, so basically project them down to the x-axis, right? Then we build that whole segment tree data structure, except with one modification, which is that when we get to one of those intervals, right, which is going to be a list of line segments, we're going to sort each of those intervals by the y-axis ranking. So if we have like a bunch of line segments here that are all in like a constant interval, we're going to order them in the sort of slab order, right? So we'll basically sort segments in each interval by slab order, right? So in other words, we sort them by the y-axis within that segment. Now notice we're not going to allow any of these line segments to cross, right? We're going to require that they're all completely, at most they will only touch at their endpoints. They'll never cross in their interiors, right? So that's an important invariant here, because if they crossed in the middle, then this trick wouldn't work. And so now, what we have effectively done is built a somewhat smarter slab decomposition. We have basically built a slab decomposition, but instead of having to store, n squared space, we're basically storing n log n space. There is a disadvantage, though, because if we want to do a query, we have to do a query inside each of these nodes at the intermediate levels of the tree until we get to the final leaf node, right? So this is effectively a slab decomposition except split into log n pieces per slab. That's sort of an intuitive way to think about this, right? Is that at each of these slabs, instead of storing like one contiguous slab for all of the that little range, we're going to have log n little bits of them, one for each level of the tree as we go up it. So how do you do a query, right? Well, if you wanted to do a vertical ray query, you just keep casting that vertical ray query into each level of this tree. Each of those vertical ray queries takes order log n time, right, per level, right? And then when you're all done, you just take the min of all of those log n queries which you've executed, and the result will be an order log squared n operation, right? So we can do in order log squared n, which means you can do very relatively fast point location. I mean, you can do better with persistence, right? And persistence would also use less memory, too. So persistence is actually a better way to do vertical ray queries in the segment tree. So it still hasn't really proven itself to be useful yet. However, we can now do these window queries. So the way you do the window query is exactly the same way that you would do the sort of interval query, right? What you do is you take the window, you chop it up into the intervals which are covered by the window, and then you run a vertical ray query, or actually a segment range query, on each of the slabs, right, that are basically left from that window. The cost of doing this is that you're going to have log n extra slabs that you have to run one of these log n cost range queries on. So the cost of doing the window query is order log squared n. And that's really the main application for this data structure, actually, even though it's often introduced alongside interval trees. And in DeBerg, chapter 10, you'll see that both of these two data structures are covered in some detail there. So if you want to look in your textbook, you can see that. So, OK. So that's segment trees in a nutshell. Any questions about this or comments? OK? All right. So with this now, I think we're pretty much done with the intervals and stab inquiries. And so I'm going to just talk about one last data structure, which is kind of a weird optimization of range trees. It's kind of a corner case. So if you recall, range trees allow us to do the following. Right? So this is just sort of like one extra kind of like bonus data structure, right? Because we have 15 minutes left. So it's just with the last bit of time, I'm going to talk about this thing. OK. So these ones, this data structure is called a priority search tree. Priority search. So for 2D, range trees are effectively optimal. For queries of the form of x0, x1 by y0, y1. Right? So we take some box, we basically locate all the points inside the box, and we're done. We have basically order n log n. Build time, so we have basically preprocess, this cost, order, query time is order log n plus k, assuming we use fractional cascading. And the space is order n log n, right? So for general queries, this is as good as it gets. There is actually a lower bound. In fact, if you actually drop that log n from there, you end up going to KD tree land, right? And you're basically going to be only getting a polynomial speedup instead of like an exponential speedup in your range queries. So that log factor is essential if you have to do queries of this form. However, there's a caveat, right? So it turns out if we restrict to half open ranges, right? So these are ranges of the form x0 infinity, right? So they're unbounded along the x-axis, but then they're still restricted along y. We can use only order n space. This is a very weird trick. Just like a weird that variations of this technique are actually how you can shave an extra log factor off of range trees in 3D. Use it to save an extra log n here in the space of a range tree in 2D, assuming that we're going to work with these more limited kinds of queries, right? And this data structure is called a priority search tree. So it's kind of like an optimization, crunch down the space a little bit, right? And then still get fast queries. You don't even have to use fractional cascading, right? It's really a very simple data structure for answering these very special kinds of queries. And to see an example where these sorts of things might pop up, maybe you have like some time series data, right? And then you want to basically find all of the points in here, right? So you have like some interval, you want to find all of like these sort of outliers or all of like the high signal points inside some massive chunk of time series, right? So if the data is very large, the log factor could be very substantial, and that's where you need to use something like really tricky, like this sort of thing. So that's priority search trees. So how do priority search trees work? What do they do? They're basically a combination of two things, right? So priority search tree. They're a mix of a priority queue or a binary heap, right? So combined with a binary search tree. So they're just like a heap and a tree all in one, all smushed into like one continuous like, data structure. So you're just going to kind of mix them up, The basic idea here in this case is that it will be a heap on X and a BST on Y. So for the Y component, we're going to use this to do sort of our range searching. And then on the X component, we're going to store a heap. Right? And if you know what a heap is, right? Remember, a heap is just it's a binary tree which has the property that the value of the heap at any given node is greater than the value of the heap at its two children. Right? And so in a priority search tree, we're going to store 4 separate values per node, right? And once you know what they are, it's easy to figure out how you would build this thing. Here's the idea. So it's basically, we'll call this PST node for priority search tree node. It's going to have 4 properties. The first is we're going to store xmin, which is basically the smallest x coordinate point in data set. We're also going to store a value called ymid, which is basically the median of points along y-axis. And then we're going to store a left child, right, which will basically be a priority search tree of all nodes, of all points less than y mid, not including xmin. And then the right child is going to have the same property. All right, so this is, again, the same idea. All points greater than y mid, ditto, whatever. All right, that's the basic data structure that we're going to have. All right, so if I take some set of points here, whatever, something like this. So the idea is that we'll first sort them by y, right? And then along actually, this is too noisy, I think. All right. I'm going to do the points in black, and then I'll do the lines in like another color. All right. OK. So we'll start from the root node. I guess we'll pick this thing here. And then this will then have, this node as a child, maybe. Right. OK. And then, right. So the idea is that we'll take each of these nodes, and then the value at this node is going to be the point with the smallest x coordinate, right? So actually, I maybe drew this tree slightly wonky. Let me erase that. OK. So, all right. OK. So we start up by finding the point with the smallest x coordinate. We remove it from the data set. So this will become our first node in the tree. then we take the remaining points and then partition them by y. So this is the y value for this node here. Right? So this is our root of the tree. For its left and right child, which I'm going to draw in sort of this funny way because there's not a lot of space on the blackboard here, we'll repeat. So let's go to this side. Again, we take the smallest node out of the tree, store it there, recursively here on this side. Again. So we store that thing here. Right. So that's the idea, right? Is that we're going to basically build this tree, right? It's going to be a binary search tree on this y component, right? And on the x component, it's a heap, right? So each of these nodes has an x min value, which is strictly smaller than all of its children, all right? So, or it's strictly larger, I guess, in this case. I don't know. However you want to do it, larger or smaller. You can just pick one. It's consistent. It's fine. So building this tree is not a big deal, right? I mean, you can just apply these invariants recursively, construct this. So to intervals which so we start out by doing a query for the y0, y1 component of our range that we're going to search. So suppose we want to search maybe this whole range here, right? So we first find where the y tree and then the other y tree would land, right? So we search on y, find this tree is completely. Here, actually, let me make a more exciting example. Yeah, and actually I drew the range going the wrong way. So suppose I want to search this range. It has to go this way in this picture. All right. So if I search with this range, what I'll do is I first find where these two y nodes will diverge, right? And then that's going to be a subtree that's completely contained in them. So I start with this y node, search through the whole tree, all right? And I'll find that this subtree is completely contained in the interval, and then these nodes I have to check, right? And so what I do is as I'm searching through the tree at each node before the y is split, I have to go check if this x min is contained inside the range. If it is, I report it. If not, terminate, until I get to one of these trees, right? So these nodes here, which I'm basically going to be searching on the two y's, right? I can just charge those for the normal binary search, right? So that will basically be part of the order log n part of the query. And then when I get down to one of these subtrees, which is keyed by x, I just start marching down all of the children. And if the value of this x min happens to be contained in this range here, then I report it. Otherwise, I stop, right? And once I stop, because it's a heap, I'm done, right? So it's basically you just binary search on y, and then once you get to one of these trees, which is completely contained in the interval, you start marching down the tree until you get to one of them, which happens to be not in the interval. So that would be that its x value is less than x0, right? So that's the idea. So does that make sense? Hopefully, right?
You said it should be x min.
I may have switched min and max here. I think I maybe flipped the x value. Let's see. So I right. Think x min is the smallest x coordinate point in the data set. So once I get to one where the smallest value is larger than x0, I'm not in the range. So actually this is fine, right? Because basically if the x min here is larger, right, that's the smallest x coordinate in this entire subtree, is bigger than x naught, then that entire subtree doesn't intersect that interval, and I'm done. I don't have to search that any further. Because this is an interval going from, this is the set of all points which happen to be between x0 less than or equal to x less than infinity, right? So if I get to a point where the smallest value in this set, right, the smallest possible point, or no, yeah, I guess it should be x max. Or I can just flip the interval too. I can do an interval like this, right? Yeah. Right. Okay, now I flipped it, right? Okay, dyslexia. But Yeah, no, it should be from infinity to x0, right? Or you can flip x min and x max, and it's the same thing.
Okay, yeah,
Right.
that makes more sense. I mean, you still
Right.
drew the
Yeah.
tree assuming it was x.
Exactly. Yeah, yeah, I mean, the original way I had this was I wanted to actually do it on y. Basic idea is the same. You can also look it up in your textbook too, right? So this is all in DeBerg chapter 10. Next time, we'll probably move on to maybe some more advanced or like kind of specialized topics. Also for projects, I'm going to give out the actual like final deadline for assigning that and like what's going to be required. So I'll send out some stuff tonight. Other than that, yeah, I think this is probably good enough, and we'll just call it a day. So.